In this video, we are going to talk about second order differential equations. Okay, we are going to introduce the concept of second order differential equations, and we'll talk about the linear homogeneous second order differential equations. Okay, now a differential equation of these forms: a d square y dx square plus b dy dx plus c y equal to 0, a d square y dx square plus b dy dx plus cy equal to f of x is called a linear second order differential equation with constant coefficients, where a, b, and c are the what? Constants. Now look at the difference. These left hand sides are the same, but the difference is in what? The right hand side. If we have the right hand side set equal to 0, it is called homogeneous. And if we have the right hand side set to some other expression or term, it is called non-homogeneous. Okay, this is homogeneous. All right. So this is it. This is the point. So they are linear second order differential equation. So this is homogeneous differential equation of the second order and non-homogeneous differential equation of the second order. Now I am going to start talking about homogeneous second order differential equations. So in the next video or in successive videos, we are going to see that of non-homogeneous differential equations of the second order. Now, we can write this in D operator form or operator D. D operator. In D operator, D, capital letter D, is D ds. And D squared is d squared ds squared. This is the point. So if this is so, it means that this very equation will now be a, in place of d squared ds squared, I can write what? D squared. A d squared y, okay, plus b dy, that's d and y, because d ds is this. So dy plus cy equal to what? 0. Y is common, so I can write this as a d squared plus b d plus c times y equal to what? 0. From this equation I will have here, let me call this equation 1. Let me call it equation 1. In place of d, I'll write m. Okay, I'll write what? M. A m squared plus bm plus what? C. To get the auxiliary equation, we'll set this to 0. So this equation is what we are going to solve. Okay, and we will obtain two values for n because it is quadratic. So we are going to obtain two values for n. So just understand what is going on here. We can go straight. If a differential equation is given to be solved, we can go straight from that differential equation to obtain the auxiliary equation. From this equation now, we can easily get the auxiliary equation. Okay, from this differential equation, we can get this by taking d squared y dx squared as m squared and dy dx as n. That is just the point. So we may not always need to go through the d operator form before getting to this stage. From here, we can get this. You get it? Now, when we have gotten this auxiliary equation, what is the next thing to do? The next thing to do is to solve the equation. Solving this auxiliary equation will produce two values for m. Okay, because it is quadratic. So let's say m is equal to alpha and m equal to what? Beta. So the solution to the equation actually has three forms in which it can exist, but the solution that we need depends on alpha and beta. This is what I'm saying. In the case, okay, here we have case 1, real and different roots. Okay, here alpha and beta are real numbers and they are different. Let's say alpha equal to 2, beta equal to 4, for example. The solution to the equation will be y equal to a e to the power of alpha x plus b e to the power of beta x. This is the first case where the roots are real and different. Also, we can have real and equal roots. In this case now, alpha and beta are the same. Let's say m equal to 2, m equal to 2. That's m equal to 2 twice. What would be the solution to that very differential equation? This is it. Y will be equal to e to the power of alpha x. In this case now, we are saying that m equal to alpha twice. You get the point? So y equal to e to the power of alpha x into ax plus b. This is the general solution of a second order homogeneous differential equation, whereby we have the same roots, two real roots, okay, of the auxiliary equation. This is the third case. You can have complex roots as well. Complex roots. So if the auxiliary equation produces a complex root, let's say m equal to alpha plus or minus I beta. This is a complex number. That's alpha plus I beta or alpha minus I beta. You get the point? What would be the general solution to that differential equation? It is this: y equal to e to the power of alpha x, that's this, into a cos beta x plus b, this is b, not beta, sine beta x. A, b, as we have it here, they are constants. So to obtain the particular solution, we will now make use of the initial condition in the case where the problem is an initial value problem. So this is it for real and different roots. This is it for real and equal roots, where the alpha and beta are equal. And when we have complex roots, this is the form of the general solution. Okay, in the next video, I will solve homogeneous differential equations, okay, and we'll see how each of these works. All right, so in the case where we have real and different roots, I'll explain this by solving a problem, and I will do the same for this other two. Just keep following. I'll see you in the next one. Don't forget to subscribe and like and share this video to your friends and your classmates.